Alright, in this video here we're going to talk about the cancellation properties of inverse functions. So if you haven't watched the video that I did on the definition of an inverse function, you might want to check that out before you watch this one, just so you understand what we mean when we're talking about inverses. But assuming that all of the things for the definition of an inverse function are true, like the f of x has to be a one-to-one function with a certain domain and a certain range and all that stuff. And again, I explained that in the video I did just on the definition of an inverse function. But assuming all those things are true, then f inverse of f of x is going to equal x, and the other way around, f of f inverse of x is also just going to equal x, right? The original function f and the inverse function. Now, when you do a composition of those two functions, and if you didn't see the video I did on composition of functions, you ought to, because it's really cool. Right, but it's also necessary to understand this. Right? When you do a composition of a function with its inverse, they just cancel each other out, and they just give you x, whatever that input was originally, that's what you get. Right? And again, in the video that I did on the definition of an inverse function, we saw in some of those arrow diagrams, 5 goes to 2, 2 goes back to 5. When you do the function and then its inverse, one right after the other, you get back to the original input value that you started with, which is what these things are saying. F inverse of f of x equals x. All right, if I do the f function first, get the output, and then plug that into the inverse function, it gives me back the original input that I started with. And it doesn't matter which order you do that with inverse functions. If function A is the inverse of function B, well, that means that function B is the inverse of function A, right? It's a mutual relationship. They're inverses of each other. So it doesn't matter which order you put them in when you do that composition of functions. You get a cancellation, and you end up with just an x, right? And then when I did that video, if you've seen it on composition of functions, I said that usually when you do a composition of functions and you switch the order, almost always you get a different result when you do that. The exception to that is when you do a composition of inverse functions. In that case, when you switch the order, you just get x. You get the same thing each time, right? That's like the exception to the rule for composition of functions, right? And so basically what we're saying here is that a function and its inverse will cancel each other out. And we use that all the time when we're solving equations, right? Think of just a real basic equation, like x plus 5 equals 7, let's say. Well, if I want to solve that equation, what do? I subtract 5 on both sides. I do that because plus 5 and minus 5 are inverses of each other, right? They cancel each other out. So that's what I do when I want to get that x by itself and I have the x plus 5. I do the inverse of plus 5, which is minus 5, and that leaves me with just the x, right? So like the f function would be a plus 5, the inverse function would be a minus 5. It leaves me with just x, right? We don't think about it when we're solving equations. We don't think about it in terms of doing inverses, but really that's what we're doing, right? If I have like x squared equals 4, well, what's the inverse of x squared? It's the square root, and so I do the square root on both sides of the equation, and the square root cancels out the x squared because they are inverses of each other. All right, so we use this cancellation properties kind of a lot when we're solving equations, even though we don't always realize that that's what we're doing. Right, now, the converse of this is also true, right? Meaning, if I'm checking to see whether or not two functions are inverses of each other, which is what this example here is asking us to do, if I want to check to see if two functions are inverses, well, if I do these two equations here, if I do these two different compositions of functions, and they both cancel out and just give me x, that means that those two functions have to be the inverses of each other, right? This is only going to happen, where I do the composition of functions and I get x each time. That only happens if the functions are inverses. Right, so for this example here, show that f of x equals x to the third power and g of x equals x to the 1/3 power are inverses of each other. Right, so if you have to show that two functions are inverses, you do these two things. You do f inverse of f of x, show that that equals x. Then you do f of f inverse of x, show that that also equals x. If they both do, these two functions are inverses of each other. All right, so let's do that. F inverse. Well, that was a big one I wrote there. F inverse of f of x is going to be f inverse. Oh wait, let's not do it in those terms because we don't know that these are inverses yet. So let's do f of g of x. Right, we're going to have to do the composition of these two functions both ways. We're going to have to do f of g of x and then also g of f of x. Right, and again, if you haven't watched the video that I did on composition of functions, if you don't know how to do a composition of functions, you might want to pause this and watch that video so that you understand what we're doing here. But when you're doing a composition of functions, basically you're taking one function and using that as the input to the other function. So f of g of x is going to be f of x to the 1/3 power. Right? So that g of x function, x to the 1/3, that becomes my input into the f function, and the f function says take whatever's in those parentheses and raise it to the 3rd power. Right? So I do x to the 1/3 power raised to the 3rd power. Right? So again, I'm taking this g function, x to the 1/3, and putting that in place of the x in the f function and raising it to the 3rd power. So it's x to the 1/3 to the 3rd power. And then if you recall the rules of exponents, when you have a power to a power, you multiply them together to simplify it, and 1/3 times 3 equals 1. So I get x to the 1st power, which just equals x. Right? So f of g of x just gives me x. The 1/3 power and the 3rd power canceled each other out. Right? That's a clue that these are inverses, but it has to work both ways. Right? So you do have to do both of these, f of g of x and g of f of x. They both have to give you x in order for them to be inverses. Right? Sometimes one of them will give you x, but the other one will not. Right? So you have to check them both. Right? So g of f of x is g of x to the 3rd power. Right? I'm taking my f of x function, which is x to the 3rd, and using that as the input now to the g function. Right? I'm replacing the f of x here in these parentheses with what f of x is equal to, which is the x to the 3rd power. All right? And then I go to my g function, which says whatever's in the parentheses, I raise to the 1/3 power. So I'm going to get x to the 3rd power, right? That's what's in the parentheses, raised to the 1/3 power. Right? Notice what I end up here with, my last steps are similar, but they're switched around because I'm doing the composition backwards. This is x to the 1/3 to the 3rd. This is x to the 3rd to the 1/3. But the result is the same because still a power to a power I multiply, and 3 times 1/3 still gives me 1, so I get x to the 1st power, which just equals x. And since both of these two just equal x, therefore these two are inverses. Right? So if you were doing a problem like this and it was like a homework problem or something, you probably wouldn't want to leave it like that. You would then want to maybe write a sentence and say, since the two compositions of functions both equal x, therefore x to the 3rd and x to the 1/3 are inverses of each other. I'm not going to take the time to write all that up here because 1, I'm lazy, and 2, I don't have enough room on the board. So there you go. All right, so those are the cancellation properties of inverse functions. So x to the 3rd, x to the 1/3 are inverses because when I put them together, or I do one after the other, I raise something to the 1/3 power and then raise it to the 3rd power, they cancel each other out. They give me just this base number here, or the other way around, if I raise it to the 3rd power and then I raise it to the 1/3 power, I get back that original number that I started with. All right, so that's what we mean by the cancellation properties of inverse functions. And again, we use them a lot when we are solving equations. It's one of the things that allows us to solve equations is using inverses to cancel stuff out. All right, so I'll be doing more videos also on inverse functions of how to, if I'm given a function, f of x equals x to the 1/3, how do I figure out, if they don't tell me this, how do I figure out what the inverse of that function is? So if you need to find stuff like that, make sure you check out the video that I'm doing on that one as well.